Okay, my friends. Thank you. Reviewing quickly 1.1. We talked about matter, right? I gotta turn this thing down. I can hear myself echoing. Okay, how's that? That sounds a little bit better, right? You can still hear me? Not too loud? Shh. Definition, please. What does matter mean? What is matter? Give me your hands. Give me your hands. This is for. This is my signal for you. Raise your hand. Sir. Takes up space. Space. And has what? Mass. Good. Okay. Talked about that. We spent some time talking about mixtures and pure substances, right? What's the difference? If I have a mixture versus a pure substance with a raised hand. And I'm curious, I'm not going to pick on the first person here to raise their hand. I want to see, do you know? These are some things you should know from 1.1. This is my reviewing. To see, did you catch the pieces you should know? And you may see this again, say, maybe a week from today, right? Okay, what do you think, Charlie?
Mixtures combination of two or more substances.
Good. Beautiful. So a pure substance is just one something, right? Where a mixture, we've taken two or more of them and put them together. Beautiful. Okay? I can take mixtures, and by the way, when I mix them together, this is kind of coming into today's lesson a bit, to take pure substances and make a mixture, physical change or chemical change. Don't say it out loud. I want you to vote with your hands. If I take pure substances and make a mixture, is this a physical change or a chemical change? You ready? If you think it is a chemical change, please raise your hands. Okay? If you think it's a physical change, please raise your hands. So there's some indecision, but yes, it is a physical change. Why? Why? With a raised hand. Why is it a physical change to make a mixture? I only got one hand. Is that it? No one else knows? 2 hands? 3 hands? Why is it a physical change to make a mixture from pure substances? Why is it a physical change, Stephen? Beautiful. I can still tell the identity. And any other expansion on that, Ben? It doesn't change its composition. In other words, it's still what it was. We've just put them together in the same place, right? Whereas if I take 2 pure substances and mix them together to form a compound, then what has happened? Chemical change, right? Physical change versus chemical change, okay? So even though a compound is 2 or more pure substances put together, the big difference is there is a reaction, a chemical change, okay? Good. A mixture, remember, we could divide into 2 pieces, the homogeneous and a heterogeneous. These are meaning same and different, right? Homogeneous is the same all the way through it, evenly mixed. And heterogeneous is very easy to pick out the different pieces that are there, right? Good. Heterogeneous. Yes. Yeah, because different. The same. Yes, sir. Good. All right. That's a good review of 1.1. So, let's talk about physical properties. Physical properties. Let's start by defining. What is? With a raised hand. What is a physical property? Sir? Okay, something you use to describe it. I like that. Something what? You can see or feel. Okay. A characteristic. You thought you were going to say? Oh, no. Okay. I thought you had your hand up before. Okay. Good. How does your textbook define a physical property? It's right there in the beginning of this section here. What does it say, Ben?
Physical properties are those that don't involve changes in composition.
Okay. So they're going even a little more broader than what you all were saying. It doesn't involve changing in composition. In other words, I don't have to change this matter to see these physical properties, right? So you all talked about things you could see and feel, these characteristics. You're correct. Okay? Some examples, please, of physical characteristics. I'll just take a raised hand for me if you don't mind. Raised hand, what do you think?
The color.
Color. He stole your blue, man. That's rough. That's rough. Okay? So color. What else? Yes? Smell. It's a great one. Sir? Texture. This is like some of the very same things that you were looking at in your lab the last 2 days, right? Good. Okay, what else, sir? Shape could be. I would. Can I take you towards state of matter instead of shape? Like solid, liquid, gas? Which would kind of be what you're saying. You know, because I could take something and change its shape relatively easily. It's not going to tell me too much about it. But if you were to tell me it was a solid or a liquid or a gas. And by the way, this is one that a lot of folks don't like. In other words, let's take our good friend water, right? H2O. To take water, an ice cube out of your refrigerator or freezer. I keep ice cubes in my refrigerator, not freezer, in the world. And I take it out, and I put it out on my hand. What starts to happen to it? Melts. Good? I take that same water then in my hand, and I dump it into a pot, and I boil it. Heat it up until it starts to steam. Becomes a gas, right? Solid, liquid, gas. Has this water undergone physical changes or a chemical change? It's a physical. It's still water. Please hear me. This is one of the harder things for folks to get because they think, wait a minute, haven't you done something to this? Sure. All you've done is just change its temperature. It's still water. Doesn't change what it is. Its actual components of H2O doesn't change that. Okay? So change of state is a physical property or a physical change. Okay? What else? Anything else you can think of? Sure, okay. Hardness. Density, I would be very fine with that. We'll talk about density a little bit today. It's volume, sure. Anything else? These are good. Very solid, my friends. No gaseous learning here. Sorry, it's as good as it gets. All right, good. They're like, really? Is that it? That's what we're going to be dealing with all year, eh? Yep, sure enough. All right. Well, before we move on, a quick peek at chemical properties. Your textbook doesn't give you a super nice list. They're over here on page 38 is when they talk about it. Okay? So let's take a peek on page 38. Chemical properties. How does your textbook define what a chemical property is? Remember, physical property, something that you could observe without changing the matter, right? Without changing the substance. What about chemical properties? A change in the composition. Okay? So in order to see chemical properties, you have to actually react them. Does that make sense, my friends? Okay? No reaction for physical properties. Yes, reaction for chemical properties. Okay? On page 39, they show you some examples of this, right? They show you bromine reacting with some metals, with aluminum here in this case, fizzing up, bubbling over. Iron reacting with oxygen to make iron oxide, which is basically rusting, but this is happening much quicker here. We have water being broken apart into its hydrogen and oxygen. That's what's happening in the third picture there. We'll do this together, you and I. Yeah, to make some oxygen and hydrogen. It's just bubbles, gases, clear gases. Yeah. I was anxious to blow things up. No, hydrogen's pretty dangerous. Yeah, in large quantities. And then hydrogen peroxide in the bottom here, breaking apart. So these chemical properties, right? You must see them react in order to see these chemical properties. Okay? Sure. Does it react with oxygen? Is basically what rusting is. Yes. Sure. Baking soda vinegar is reacting to produce carbon dioxide bubbles? Absolutely. Yes, sir. Okay. Fantastic. Any questions in regards to physical changes, chemical changes, physical properties, chemical properties? Any questions there? No questions? Good. All right, do this. Stand up for a minute. Stand up. Stand up. I want you to stretch a little bit. I'm going to make a pause. Okay. We're back to talk about density. This is getting us ready for our lab tomorrow. Density. You are my density. I mean, destiny. You heard this before? Oh, Back to the Future. It's a classic movie. Early 80s movie. Yes, that's what Michael J. Fox's dad says to the woman he's going to marry. You are my density. I mean, destiny. Kind of blows the line a little bit, but it's a great movie. Be nice. 2 more years. That's when we're going to be at the same time when that second one is. No, 2016. I'm pretty sure. Yeah, pretty sure. 1986 was the first one. So, yeah. Yeah. Okay, density. 2 pieces. 2 pieces to density. And I'm looking to see, do you know, what are the 2 pieces that make up density? What do you think? Good. So it's the mass. And weight and mass are similar. Remember, we talked about that, right? And what else? Volume. Okay? So it is a measure of these 2 things, mass and volume. Okay? Anyone know the equation? Density equals, Good. M over V. Mass over volume. What units do we use for mass? We use grams. What units do we use for volume? You can use cubic centimeters, cc. We don't usually use it in chemistry, but you could. You're saying it right. Yeah, milliliters. Milliliters. That is our volume that we use. So this is a classic picture that they show you here on the top of page, what is that, 34? That this lady's got this box, right? Same sized box. One is filled with rocks. One is filled with cotton balls. Or something like that, as they used to be back in the day. Plastic foam balls, excuse me. Notice they have the exact same volume, right? The boxes are the same size. But which one has more mass? Definitely the rocks, right? So therefore, they have different densities. Okay? The lab that I'm going to ask you to read to prepare for tomorrow, we're going to look at pennies. This is over on page 36 and 37. We're going to look at pennies. Pennies have a copper covering. That's what we all think they're made of. But actually, most of them are made of nickel. Anybody know why? It's cheaper. Yeah. Pennies do, it does cost more to make a penny than a penny is worth. It's fairly crazy. Who knows? Who knows? Right. But now pennies don't do much. Very true. Very true. I'm with you. Nice. 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 But back in the day, there was a point where pennies were made of a different substance on the inside. And what we're going to do in this lab is see if we can't figure out, based on their density, when that occurred, when that change happened. Okay? Because it became too expensive to make them out of what they used to be made out of, and now they make it out of something different. So this is kind of a lab, and we're going to use the density of these pennies to help figure that out. Okay? That's a little teaser for the lab coming up. Are you comfortable with this? Okay? So you would find how you would, if you want to solve the density or find the density of something, you would take its mass that you measure and divide it by the amount of volume that it's taking up. Those of you that you have your textbooks, let's look in the very back. On page 850, I want you to see this reference table, page 850. Sir?
When you find the density, it's grams over milliliters.
Yes.
What's the final unit that you use?
Grams over milliliters.
That's it?
That's it, yeah.
So it would be like 200 grams over milliliters.
Yes, sir. Yep. Mm-hmm. Yep. Grams per milliliter is how you say it. Yeah. You see this table on page 850? And it actually continues over onto page 852 and 853. This is all the elements. Like all the elements up on that periodic table are listed for you here in this reference table. And they're giving you some properties. Most of these are physical properties. Some of them are chemical. But most of them are physical. If you look in the very middle of that table, what property do you see listed there that we just finished talking about? I'm speaking about the column that's 1, 2, 3, 4, 5, 6, 7 over from the right, or from the left. What do you see listed there? Density. This is such an important characteristic of these elements that they put it here in this table. Okay? Some of the other things they give you are what are their melting points and their boiling points. We'll talk about atomic mass and atomic number. You'll understand what all these things are by the time we finish here. But density is such an important characteristic that, again, it's one of the ways we can identify what an element is, whether it's this or whether it's that, based upon its density. Questions? No worries? Sir? Sure. Right, yeah, the radiation. It wouldn't kill you immediately, but yeah, it would start some damage in your cells that would lead to cancer. Absolutely. Yeah. Okay, last but not least, let's talk about conservation of mass. Going back. Yes? That's a great question. Did you guys hear what he said? If radiation causes cancer, why do they use it to kill cancer? That's it. It's all math, brother. No, does anyone know? It's a great question. It does kill the cancer cells. Well, the thing is that, no, they mostly try and target the actual spot of the cancer cells. Yeah. In other words, when you have radiation treatment for cancer, they don't just put you in a room and say, here's radiation that goes all over you. They try and focus it on a very specific spot. Yeah. So does it? Well, no. Sometimes they do. It just depends on what kind of treatment they're giving you. But yeah. So they're trying to focus it very specifically. But does it cause other problems? Absolutely. If you know anybody who's been through radiation treatments, it's not fun. Significant side effects. But it's better than dying. So. Okay. Law of conservation of mass. And I'll even just put matter here too, because it means the same thing. And your textbook uses them interchangeably. 45, right? We're done with 45? You guys are rolling today. You're with me. Good. I like it. All right. If you had to sum up the law of conservation of mass or matter, could you do it in a sentence, in a phrase, with a raised hand? If you can do it, tell me about it. I want to see who knows. It's good. It's good. I'm encouraging those of you who haven't raised your hands. Yeah, jump in here. I want to hear from you. I want this to be a participatory class, not just Mr. Hesse yakking at you. What do you think, sir?
I guess, like, in the first moment before the reaction, like a number of something of matter.
Sure.
After the reaction, you'll have the same number.
Fantastic. So he says, whatever matter you're starting with in a reaction, you're going to end with that same amount. Beautiful. Any other explanations? Yes, ma'am. Not created or destroyed, right? It's just changed. I have a hard time believing this when I'm trying to find my golf ball, because I swear there are times that I've destroyed this matter and I cannot find it. It drives me crazy. I mean, well, some of us hit the ball really long and hard, yes, so it could, but no, it can't be. Drives me crazy. Can't find those stupid golf balls. All right? I'm sorry? Well, yeah, there are different ways you can, but it's still, if they're in the woods, which mine tend to go at times. Not Ben's. Ben's is always solid. Both Ben's are very solid. Mr. Hess is all over the place. Okay? So, neither created nor destroyed, and that is a key component. Nor destroyed. Just change. Okay? What things can mass change into? Can matter change into? No, that's a bad question. Exothermic, endothermic. You've heard of this, right? You read this, okay? Exothermic means releases heat. Endothermic means absorbs heat, right? Okay? Mass can become energy. Okay, that's what Mr. Einstein, that's like his famous E equals mc squared equation, is saying it can. Mass can become energy. It's the same thing, right? But most of the time, we're not splitting atoms and doing that. We're simply giving off or releasing the energy needed to bond these things or to break the bonds between them. And that's what that exothermic or endothermic is. Okay? So this is a key point. If we are capturing all the gas, all the everythings from a reaction, whatever I start off with in mass, I must finish with. Okay? Any questions there? Because this is a foundational property. We'll use this when we start writing reactions. However many carbon atoms you've got to start with, you're going to have that many carbon atoms to end with. Okay? Have to balance them. We'll talk way more about that in the future. Questions that you have for me? Sir.
The guy who discovered this.
Yes. Shh. Sorry?
The guy who creates this law.
Mr. Boyle, I think, had a huge part to play in this. I think Le Chartier had some work with that. The French and the English were doing some work with that. I can't remember 100% who it was. I think Lavoisier, I know he did a lot of work on that. And Mr. Boyle, I think, did as well. This was all in that around 1800s where they were doing a lot of work in this chemistry stuff. I can't put my finger on it exactly which one it was. But I think Lavoisier was who did it. Okay? Very solid, friends. Other questions? There will be some more, but yeah, this is significant pieces. Yeah. We'll bring in the lab. We'll bring in the video that you all watched. Yeah, absolutely.
Can we watch the video again?
Oh, please. You can watch it 1,000 times. Yeah, absolutely. Okay. Let me show you what is going to be your homework that you can even start these last couple of minutes. By the way, I pulled up, this is Schoology, so you can see over on this side on my page, you see when the test is, right? I don't know if you all noticed this already, your calendar, upcoming things. And here are the assignments. So the lab report is due tomorrow. And then my assignment for today is these questions at the end of chapter 1.2. So it's page 42, number 6 to 9. Here's some practice on using physical and chemical properties. 6 through. 6 through. Okay? And we've got about 3 minutes here. You could probably knock out a few of these right now until that bell rings.